143.024. Basically, your factor of safety is equal to 160 times 10 to the power 3 or times 10 to the power 6 divided by 143.042 times 10 to the power 6. Okay, so 160 power 6 divided by 143.042 power 6 is equal to 1.118. Okay, so your that is your factor of safety basically. Okay, so it can be factor of safety considered for buying cheap steel, okay, from a certain country. Yeah, you need to have factor of safety in or it can be manufacturing processes. Okay, now by the way, this is only considering the considering the where is my cross section? Yeah, by considering the structure failing at the intersection over here, right? But we did not take into the factor of the fillet radius. Okay, so if you have a fillet radius, you probably have to you get this value over here, right? Probably you have to do a multiplier. Okay, you have to multiply a certain number. Okay, you have to multiply a certain number on your principal stress to take into consideration the safety factor. Right. So if you were to refer back to your textbook, okay, I'm going to go into the textbook. And we are going to look at chapter 8. Okay. So we have been doing is we have been just applying what we have learned. So normal stress, shearing stress, and Mohr circle into chapter 8. Okay. So if you look at chapter 8, initial we already have done shaft, right? You can see that it's shaft. Then we have done beams, which we have just covered. Okay. Then we have also done, okay, so this is gears, we have done that, and then compound loading like this. Okay, so there are three different types of loadings. Okay, shaft, the shaft loading, the unique thing about shaft loading that we learn is there's no axial load. I repeat again, the shaft loading has no axial load. Then the week before that, we learn compound loading like this. Okay, like what you see, so we can have axial load, any loading. The distinct effect about this chapter over here is when to determine is a shearing force, an axial load, or a bending moment, or a torque. Okay, so we have done the most difficult. Then today we have done a design of beams. Okay, which is the easiest. Shaft can be a little bit difficult, so we have done beams. Okay, so today we have covered beams like this. Okay, so that is the end of chapter. In fact, chapter 8 is the most important chapter. Okay, in regarding structure design. Okay, so if you don't know your bending moment and your shear force and your Mohr circle, you cannot do chapter 8. Okay, so we are going to go into now chapter 8. You can go away with 2D Mohr circle. Next, we are going to do 3D Mohr circle. Okay, we're going to go into 3D Mohr circle now. Okay, so this is done on one big chapter. I'll put down here for you to reference. So this is end of chapter 8. Okay, so now we are going into 3D Mohr circle. Okay, now 3D Mohr circle again is not more difficult than 2D Mohr circle. If you can do 2D Mohr circle, you can do 3D Mohr circle. Okay. Okay. And I'm going to highlight to you why 3D Mohr circle is important also. Okay. So with 3D Mohr circle, so I put down here 3D Mohr circle. So with 3D Mohr circle, right? The analysis is to determine the principal stresses. Right? So in real life, okay, in real life, we have to always apply 3D Mohr circle. 2D is just to learn the fundamentals. Okay, we have to use 3D Mohr circle. So just to briefly recap, right? So if we have an element over here, I have to draw a bigger one. Okay, so let me draw a transformation first. X, Y, and Z. Okay. So if we were to draw a 3D element, right? So over here, the XY plane this is known as our in plane, right? Whereas our our YZ plane is our out of plane, and our XZ plane is also our out of plane. Now, if we orientate, I probably did this with you guys before, but I want to go through this in case you forget. Now, if now our structure is in this orientation now, okay, the transformation is still the same, by the way. Right? So this surface over here, which is our XZ plane, because of the bigger surface area, this is known as the in plane now. Right? So this is our XY plane, and this is out of plane. So in case you come across question that orientates the element differently, it's just trying to highlight which is the in plane and out of plane, and it's all dependent on the surface area that you see. Okay, that's it. Okay, right. So now let's consider. So this is just to recap or recall or revise what is in plane and out of plane. That's all. Just to recap. Okay. So now we are going to consider an element now. Okay, we're going to consider an element now. And the orientation of the element is this way. Okay. So this is X, Y, and there's Z, right? So now the element is in this orientation. Okay. Okay. And we know that this direction is our stress X. Okay. This direction is our stress Y. And then this direction over here, this is our stress Z. And there's also shear also. If I were to draw our shear direction, okay. So this is shear right? The intersecting plane is x, the right direction is y. Okay, this is shear y x. Okay, so that's one shear component. The other shear component, okay, will be in this direction. Oh, I should not draw the arrow like that. So this is the other shear direction. So this one will be shear. The intersecting plane is x, okay, or the plane intersecting the x-axis. So this is z. Okay, so this is shear. The intersecting plane is in z. Okay, and then this is in x direction. And then we have one more. Right. So over here, the shear, the intersecting plane, the plane will intersect the y-axis. Okay, and this is z. And over here, the intersecting plane is in z, and the shear force is in the y-axis. Okay, so the case that we're going to consider now, okay, that from here on I write down, we're going to have three cases, but the principal ruling case is when the orientation, okay, when the orientation of the element okay is such that shear xy is equal to shear yx, okay, and shear yz is also equal to shear zy, and the shear xz is also shear zx, and they are all equal to 0. Okay, so i.e. there's no shear component over here. Okay, everything is equal to 0. Then the element is at its principal plane orientation. Okay. So whatever condition that we're going to draw later on, okay, there's no shear at all. Okay. So let's look at condition number 1. Okay, let's look at condition number 1. Okay, so let's look at condition number 1. Okay, let's look at condition number 1. So condition number 1 is such that stress X is greater than stress Y, and both are positive. Okay, and stress Z is equal to 0. Okay, so let me draw the element. Okay, so the orientation is still the same. Our transformation X, Y, Z. Okay. Then we have okay. So you have over here stress X, over here stress Y, okay, and then we have our stress Z is equal to 0. Okay, so we're going to draw our surfaces now. Okay, so this is our hold on. Okay, so this is our point X, point Y, and point Z. Okay, so we're going to draw this out now. Okay, so I'm going to draw a circle or 3 circles. Okay, So again, this is